Hello students, this is Divya, Assistant Professor of MCA Department from Erode Engineering College. Today we are going to see about data structure and its algorithms. So first of all we are going to see about what is data structure. So first, data means collection of raw facts. Data structure is representation of the logical relationship existing between individual elements of data. Data structure is a specialized format for organizing and storing data in memory that considers not only the elements stored but also their relations to each other. So this is a classification of data structure. So data structure is divided into two types. The first one is primitive data type and the next one is non-primitive data type. So in primitive data types we are having a data types called integer, character, float and pointer. In non-primitive data types it is divided into two types. One is array and another one is list. So in an array we are having three types of arrays. The first one is single dimension array and then two-dimensional array and the final one is multi-dimensional array. In list it's divided into two types. One is linear list, another one is non-linear list. So linear lists are called as an stack, queue and then linked list. In non-linear lists they are trees and graphs. This is a classification of data structure. So first, primitive data structure. There are basic data structures and directly operated upon by the machine instructions. Data structures that are directly operated upon the machine level instruction are known as primitive data structures. So such as integer, floating point number, character constant, string constant, pointer, etc. fall in this category. The most commonly used operation on data structure are categorized into these types. First one is create, selection, updating, destroy or delete. And then non-primitive data structure. The data structures that are derived from the primitive data structures are called non-primitive data structures. Non-primitive data structures on structuring a group of homogeneous, that means same type or different types of data items. So this is divided into two types. First one is linear data structure and another one is non-linear data structure. So non-primitive data type is nothing. It is derived from the primitive data structure. First, abstract data type. So it is also called as an ADT. ADT is a collection of data and set of operations that can be performed on the data. It enables us to think abstractly about the data. We can separate concepts from implementation. Typically, we choose a data structure and algorithms that provide an implementation of ADT, that is abstract data type. And first one is linear list. Linear list is a data object whose instance are form of E1, E2 up to n elements. So EI is an element of a list. That means next E1 is the first element and En is the last element. So n is the length of the list. When n is equal to 0, it is called as an empty list because there is no elements presented in the list. When the value of n is 0, there is nothing in the list. E1 comes before E2, E2 comes before E3 and so on. So E1 and E2, E3 are mentioned here as the first element, second element and then third element. Next, implementation of linear list. So first is array based, that means formula based. Uses a mathematical formula to determine where to store each element of the list. That means where, in which memory location it want to store. And then next is linked list. It is based on the pointer. The elements of a list may be stored in any arbitrary set of locations. Each element has an explicit pointer to the next element. And then next is indirect addressing. The elements of a list may be stored in any arbitrary set of locations. Maintain a table such that the table entry tells us where the element is stored. And next one is simulated pointer. Similar to linked representation, but integers replaces the C++ pointers. Formula-based representation. Formula-based representation uses an array to represent the instance of an object. Each position of the array, called a cell or a node, holds one element that makes up an instance of the object. Individual elements of the instance are located in the array based on a mathematical formula. For an example, simple, and then it is used by formula. So here is an example: location I is equal to I minus 1, which says the ith element of the list is in position I minus 1. We also need two more variables, length and max size, to completely categorize the list type. Linked list. One way to overcome the inefficiency problem of previous approach is to assign space on the base. No space will be assigned if there is no need, and whenever there is a need, another piece of space will be assigned to an element. We cannot guarantee all the pieces of space assigned at different times will be physically adjacent besides the space assigned for the elements. We also have to keep track of the location information of previously assigned pieces. In a linked representation, each element of an instance is presented in a cell or node, which also contains a pointer that keeps information about the location of another node. This is called as a linked list. Here is an example for a linked list. So first it is called as a link field, and then there is a data field. The first element to the nth element, that is represented as E1, E2, E3 up to En. So the field are connected with one by one. So this is called as a link field. Circular list. Some application might be simpler or run faster by representing an list as a circular list and adding our head node at the front. So circular list has and it has front node and the last node is connected. In front node there is two nodes. One is a data node and another one is an address node. The address of the next node is connected in the previous node, and then the last node is also connected with the first node. And the first node has the head will be empty because it does not store any address of the another node. Next, doubly linked list. So doubly linked list is a type of linked list in which each node, apart from storing its data, has two links. The first link points to the previous node in the list, and the second link points to the next node in the list. So it is not like a linked list and then circular linked list. It has three nodes. One is a data field. In node it is divided into three fields. First center field is a data field, and then first field is an address of the previous element, and then last field is an address of the next element. The first node of the list has its previous link pointing to null. Similarly, the last node of the list has its next node pointing to null. The two links help us to traverse the list in both backward and forward direction, but storing an extra link requires some extra spaces. So here is an example for a doubly linked list. The first node, first field will be null, and then second will be data, and the third field will be connected to the next field. The third field contains the address of the next node. In the second node, the first field will be address of the previous node, and then second field will be data, And then third field again it is stores the data source address of the next node. In third field, the first field is an stores address of the previous node, and then second field stores data, and then third field is null because it doesn't store any addresses. Indirect addressing. This approach combines the formula-based approach and the top-the linked representation. As a result, we cannot only get access to elements of one element, but also have the storage flexibility. Elements will not be physically moved during insertion and or deletion. In indirect addressing, we use a table of pointers to get access to the list of elements. So here is a figure that shows an indirect addressing. Next is stacks. A stack is a container of objects that are inserted and removed according to last in and first out principle. In the push down stacks, only two operations are allowed. Push the elements into the stack and pop the elements out of the stack. A stack is a limited access data structure. Elements can be added and removed from the stack only at the top. Push adds an item to the top of the stack. Pop removes the item from the top. A helpful analogy is to think of a stack of books. You can remove only the top book. Also, you can add a new book on the top. Applications. The simplest application of a stack is to reverse a word. You push a given word to the stack letter by letter and then pop letters from the stack. So another application is an undo mechanism in text editor. This operation is accomplished by keeping all text changes in a stack. So in working with a Word document, if we are doing undo, it will remove the lastly added elements. And we have to add the element means also it will add on the last. Backtracking. This is a process when you need to access the most recent data element in a series of elements. Think of how do you find a way from an entrance to an exit. Once you reach a dead end, you must backtrack. But backtrack to where? To the previous choice point. Therefore, at each choice point you stored on a stack called possible choices. Then backtracking simply means popping a next choice from the stack. How it will implemented. In the standard library of classes, the data type stack is an adapter class, meaning that a stack is built on top of other data structures. The underlying structure for a stack could be an array, a vector, an array list, a linked list, or any other collection. So type of the underlying data structures, a stack must implement the same functionality. Here is an example for the implementation. Here we are using a push, pop, peek, and empty. Next, array-based implementation. In an array-based implementation, we maintain the following fields. An array or A of default size of greater than or equal to 1. The variable top that refers to top element in the stack and the capacity that refers to the array size. The variable top changes from 1 to capacity 1. We say that a stack is empty when top is equal to 1. And the stack is full when the top is equal to capacity 1. In the field size stack abstraction, the capacity stays unchanged. Therefore, when top reaches capacity, the stack object throws an exception. See stack array for complete implementation of the stack class. In a dynamic stack abstraction, when top reaches capacity, we double up the stack size. Linked list based implementation. Linked list based implementation provides the best dynamic stack implementation. That is, it is an efficiency point of view. See liststack.java or complete implementation of the stack class. Next is queues. A queue is a container of objects that is inserted and removed according to the first in first out. An excellent example for queue is a line of students in the food court. New additions to line made to back of the queue, while removal happens in the front. In the queue, only two operations are allowed, NQ and DQ. NQ means to insert an element into the back of the queue. DQ means removing the front item. So the picture demonstrates the FIFO axis. The difference between stack and queue is removing. In stack, we remove the item the most recently added. In queue, we remove the item the least recently added. So this is an example: back, front, and then NQ and then DQ. Next, implementation. In the standard library of classes, the data type queue is an adapter class, meaning that a queue is built on top of the other data structure. The underlying structure for a queue could be an array, a vector, an array list, a linked list, or any other collection. So type of underlying data structure, a queue must implement the same functionality. This is achieved by providing a unique interface. So here we are using an empty and then get front and then DQ, NQ, and then clear. Next is circular queue. Given an array A of default size is greater than or equal to 1 with two references back and front, originally set to 1 and 0. Each time we insert a new item, that is NQ, we increase the back index. When remove means DQ an element, we increase the front size. Here is a picture that illustrates the model. So here is a front and then back. So each time we insert a new element, it will increase the back size. So if we are inserting a new element in 1, it will increase us to 5. So first of all, there is only a 4 fields are represented. We are adding an element in a first field, it will increase us the field at backside. If we are adding remove in an element at the backside, it will increase us the size at front side. So as you see from the picture, the queue logically moves in an array from left to right. After several moves, back reaches the end, leaving no space for adding new elements. So there is a free space before the front end text. We shall use that space for enqueuing new items. That is, the new entry will be stored at index 0, then 1 until front. Such a model is called an wraparound queue or a circular queue. So applications of queue. The simple two search techniques are known as depth first search and then breadth first search. These two searches are described by looking at how the search tree will be traversed. So first is depth first search with a stack. In depth first search, we go down a path until we get a dead end. Then we backtrack or back up to the get an alternative path. So first we have to create a stack and then create a new choice point, push the choice point onto the stack, while not found and stock is not empty, and then pop the stack, find all possible choices after the last one tried, push these choices onto the stack and then return. Next is breadth first search with a queue. In breadth first search, we explore all the nearest possibilities by finding all possible successors and enqueue them to a queue. So here we have to create a queue and then create a new choice point, same as a depth first search. Enqueue the choice point on the queue while not found and queue is not empty. Next we have to dequeue the queue. Find all possible choices after the last one tried. Enqueue these choices onto the queue and then return. Tree, a non-linear data structure. Tree is a non-linear data structure that is mainly used to represent data containing a hierarchical relationship between elements. So for example, here is a family tree. So here the root node is A. It is represented in a level 0. And then B and C node are at level 1 nodes. And then D, E, F, G are called as a level 2 nodes. So binary tree. A binary tree is a special type of tree in which every node or vertex has either no child node or one child node or two child nodes. Child node in a binary tree on the left is terminated as left child node and in right is terminated as right child node. Here A is a root node. It is represented in level 0 and then B and C are child nodes. So B is a left child node and C is a right child node. It is represented in level 1. And then D and E are child node for B. D is a left child node for B and E is a right child node for B. And F and G are child node for C. So F is a left child node, G is a right child node. These are represented in level 2. Types of binary tree. Full binary tree. It also called proper binary tree or two tree, in which all the nodes other than the leaves has exact two children. So here is an example for full binary tree. So all the nodes are contains two child except the leaf node. So leaf node is nothing but last nodes. So here the root node is A and then child for A are B and C and the child for B is D and E and C is F and G. Here D, E, F, G are called as a leaf nodes. So leaf node doesn't contain any children. Complete binary tree. A binary tree which has all levels completely filled. Last level must also filled from left to right. So this is a difference between binary tree, complete binary tree. So last level must also filled from the left to right. So here the nodes are filled from left to right. So it is called as a complete binary tree. Extended binary tree. A binary tree can be converted into an extended binary tree by adding two nodes to its leaf nodes and to the nodes that have only one child. These new nodes are added in such a way that all nodes in the resultant tree have either 0 or 2 children. Next is a threaded binary tree. In threaded binary tree, the special pointer called thread is used to point to nodes higher in the tree. Memory representation of binary tree. So first is an array representation of binary tree. So first root node is stored in A of 0 and node occupies A of 5. And then left child is 2 star I plus 1, right child is 2 star I plus 2 and then parent node is I1 divided by 2. Here is an example for the array representation of binary tree. Here A of 0 contains the value of 23, that is an parent node. And next A of 1 is represented at 12, that is a child node for 23. And then A of 2 presented 11, it is a right child node for 23. And then A of 3 contains 8 and A of 4 contains 9 and then A of 7 contains 10. So linked representation of binary tree. In this representation, the binary tree represented in memory by linked list. So first we are starting from first. So the information is A. The left node for A is 3 and then right node for A is 5. So and then in 3 we are having an info as B. There is no left node and then right node. And then we are having a C as a 5. There is 0 left node and then 0 right node. So traversing a binary tree. How to traverse a binary tree? So the first is pre-order, and then in-order, and then post-order. These are the three types we are using for traversing the binary tree. In pre-order, process the root OR and then traverse the left subtree of OR in pre-order. Next is traverse the right subtree of OR in pre-order. In order, traverse the left subtree of OR in order, process the root OR, and then traverse the right subtree of OR in order. In post order, first we have to traverse the left subtree of OR in post order, and then traverse the right subtree of OR in post order, and then process the root OR. These are the three types we have to use in traversing the tree. First one is pre-order, and then in-order, and then post-order. So here is an example for in-order, pre-order, and post-order. So here see, first we are using an pre-order. So in pre-order, first we are taking a root node A, and then left node B, and then child of B is D, and then H, I, E, J, K, and then C, F, L, and G. This is pre-order. We have to use in order means H, D, I, J, E, K, and then A, L, F, C, G. In post order, we have to use H, I, D, J, K, E, and then B. After that, L, F, G, C, A. The finally only root node will be accessed in post order. In pre-order, the root node is accessed in first step. In order, it is accessed in the middle of the process. In post order, it is accessed in the final. So pre-order, info, left, right, and node. So a binary tree T is in memory. The algorithm does not pre-order traversal of T. Applying an operation process to each of its nodes, an array stack is used to temporarily hold the address of the nodes. Here is an algorithm for this process. And next is an in order. Here also we are having an info, left, right, and root. A binary tree is in memory. This algorithm does an in order traversal of T. Applying an operation process to each of its nodes, a array stack is used to temporarily hold the address of the nodes. Same as an in order and pre-order. Here is an post order. So same as this, but the algorithm will be changed. Next is an binary search tree. If T is a binary tree, then T is called a binary search tree. If each node n of T has the following property: the value at n is greater than every value in the left subtree of n and is less than every value in the right subtree. So here the root node is 38. So left side of the 38 is all the values are less than 38. In right side, all the values are greater than 38. So searching and inserting. If an item of information is given, the following algorithm finds the location of the item in binary search tree, or insert item as a new node in appropriate place in the tree. So first it will compare the item with the root node n of the tree. If item is less than n, it proceeds to the left child of n. If item is greater than n, it proceeds to the right child of n. And then it will repeat the step for 1 until one of the following occurs. We meet a node n such that item is equal to n. In this case, the search is successful. We meet an empty subtree which indicates that the search is unsuccessful, and we insert item in the place of empty subtree. So here is an example for insertion. Suppose the following 6 numbers are inserted in order into an empty binary search tree. So the first element is 40. It is fixed as a root node, and then next element is 60. It will compare with the root node. So 60 is greater than 40. So it is going to be represented in the right side of the root node. And then next element is 50. It is compared with the root node 40. It is greater than 40. So it is come to the right side, and then compared to 60. It is less than 50. So it is the left side of 60. And then 33. Now 33 is compared with 40. 33 is less than 40. So it is represented in left side. And then 55. Now 55 is compared with 40. It is greater than 40. So it comes under right side. And then it is compared with 60. It is less than 60. So it is the left side. It comes at left side of 60. And then compared with 50, it is greater than 50. So in 50, it is a right side. And then 11. First 11 is compared with the root node of 40. It is less than 40. And then compared with the 33, it is also 11 is again less than the 33. So it comes under the left side of 33. This is an insertion process of binary search tree. Here is an algorithm for location finding. Here is an deletion algorithm for binary search tree. I hope you all understand about the basics of data structures and algorithms. Thank you.